Why is it that every time physicists get close to the ultimate theory, it slips right through their fingers? Think about it. Decade after decade, we've been promised that the big unifying idea was just around the corner. Einstein thought he was close. String theorists swore they had the blueprint. Others claimed quantum gravity was within reach. Yet here we are, over a century after relativity and quantum mechanics reshaped science. And we still don't have a single framework that ties everything together. The idea of a theory of everything sounds irresistible. Imagine boiling down the whole universe into one elegant equation, a formula that explains why galaxies spin, why atoms stick together, and why you and I even exist. It would be the crown jewel of human thought, the deepest possible answer to the biggest question. What's really going on underneath it all? But here's the catch. Every attempt so far has failed. Not because scientists aren't smart enough, not because they haven't tried hard enough, but because nature itself keeps throwing curveballs. The theories look brilliant on paper, sometimes even beautiful. But when you push them against experiments or the messy details of reality, they break apart. So, why do we keep trying? Why hasn't physics thrown in the towel? Maybe because the dream is too powerful to give up on. And maybe the failures are telling us something deeper about the universe, that it isn't as simple or as neat as we want it to be. In this journey, we're going to dig into why every theory of everything has collapsed under its own weight, what scientists have learned from these failures, and whether the dream is even possible at all. The dream of a single theory didn't begin with Einstein, or even with modern science. Humans have always wanted a unifying explanation. If you go back far enough, ancient philosophers were already asking, what's the one thing behind everything else? To the Greeks, it was water or fire, or some invisible substance that tied the world together. They didn't have particle accelerators or telescopes, but they were wrestling with the same itch we still have. The feeling that the chaos of reality must come from some simple root. Fast forward a couple of thousand years, and Newton came along. His laws of motion and gravity were like magic compared to what came before. Suddenly, the fall of an apple and the orbit of the moon were the same phenomenon, described with the same mathematics. For the first time, humanity had a taste of what unification really meant. The heavens and the earth weren't governed by separate rules. They were one story. But Newton's laws weren't the end of the road. As science advanced, cracks began to show. Mercury's orbit didn't quite fit. Light refused to behave like ordinary waves or particles. The universe was hinting that Newton's neat system was only a stepping stone. And then Einstein shook everything up. Einstein's theory of relativity didn't just adjust Newton's equations. It rewrote our picture of reality. Gravity wasn't a force pulling objects together like invisible glue. It was the bending of spacetime itself. Planets weren't being tugged around the sun. They were rolling along curved geometry like marbles spiraling around a stretched trampoline. For Einstein, that breakthrough wasn't enough. He didn't want two separate rule books, one for gravity, another for the forces inside atoms. He wanted one framework that explained it all. So in the later part of his career, he devoted himself to unification, chasing what he called a unified field theory. But he refused to accept quantum mechanics, the very field revolutionizing physics at the time. While young scientists were uncovering a bizarre quantum world full of uncertainty, Einstein kept pushing for a clean, deterministic picture. And this is where the story turns. Einstein's failure wasn't just a personal one, it revealed something bigger, that maybe nature doesn't want to be squeezed into one neat equation. His struggle marks the first modern reminder of how slippery this quest really is. So, from the earliest philosophers to Newton to Einstein, the dream has always been the same: tie everything together. And each time we think we've done it, reality finds a way to remind us that there's still another layer, another puzzle, another contradiction waiting to be solved. Before we continue, let me ask you something. How many times have you had a great idea, but the moment you think about actually setting it up, it feels overwhelming? A website, The design, the pages, hosting, the logo, it all stacks up fast. That's where Odoo comes in. It's an all-in-one business platform that makes getting started simple. With Odoo's website builder app, you can get your site live in just 4 easy steps. You choose your type, industry, and goal, choose a color palette or upload your logo, add the pages and features you want, pick a theme, and you're done. From there, it's all drag and drop. You can swap images, move blocks around, change layouts, and customize everything without touching a single line of code. The best part, the first app you choose is free for life. That means unlimited hosting, full support, and no trial clock counting down. Plus, you also get a free custom domain for your first year, so your site looks professional right from the start. So, if you've been putting off that idea because of the setup, Odoo makes it easy to just start. Click the link in the description and see how quickly you can launch something today. If you want to understand why a theory of everything keeps slipping away, you have to start with the 2 great frameworks that define modern physics: general relativity and quantum mechanics. These are the twin pillars of science, and they couldn't be more different in how they see the universe. On one side, you have Einstein's general relativity. It's smooth, continuous, and elegant. It treats the universe like a grand stage where the drama of planets, stars, and galaxies plays out. Gravity isn't a force in this picture. It's the very shape of the stage itself. When something heavy like the sun exists, it warps the stage, and everything else, Earth, asteroids, comets, just follows the curves. This theory has passed test after test for more than a century. We've seen its predictions confirmed by the bending of starlight, the ticking of atomic clocks at different altitudes, even by the existence of gravitational waves. It's a masterpiece of science. On the other side, you've got quantum mechanics. This one is nothing like relativity. It doesn't care about smooth curves or elegant stages. It deals in probabilities, randomness, and uncertainty. In the quantum world, particles don't have fixed positions until you look at them. They exist in clouds of possibility, like dice rolling in slow motion, where every outcome is real until you check. And the rules that govern them, superposition, entanglement, tunneling, are so strange that even the scientists who discovered them struggle to believe their own math. But as bizarre as it sounds, quantum mechanics works. It powers the chips in your phone, the lasers in your DVD player, the GPS in your car. Without it, our modern world would collapse. Now, here's the problem. These 2 theories run the universe on different scales. General relativity rules the big things: galaxies, stars, black holes, the expansion of the cosmos itself. Quantum mechanics rules the small things: atoms, electrons, quarks, the stuff reality is made of at its most basic. They don't overlap often. Most of the time, you can ignore one and just use the other. If you're calculating how a rocket gets to the moon, you use relativity. If you're building a quantum computer, you use quantum mechanics. No conflict. But the moment you ask a question that needs both, like what happens inside a black hole, or what happened at the very beginning of the universe, everything breaks down. The math stops making sense. Relativity gives you infinite curvatures of space-time, singularities where the equations collapse. Quantum mechanics gives you fluctuations and uncertainties that make no sense in a smooth, continuous space-time. Try to combine them, and it's like trying to jam 2 puzzle pieces together that were never cut from the same picture. This is why physicists call it the incompatibility problem. It's not that one of the theories is wrong, they both describe reality with incredible accuracy. The problem is that reality itself seems to demand both at once in situations where they refuse to fit together. The incompatibility problem arises because each framework is built on completely different assumptions about the nature of reality. One sees continuity, the other granularity. One assumes determinism, the other thrives on indeterminacy. These philosophical and mathematical foundations clash whenever extreme gravity meets quantum-scale phenomena. And that's the crux of why a theory of everything is so hard. It's not just about finding a new formula, It's about reconciling two pictures of reality that look like they were painted in completely different styles. If you line up the fundamental forces of nature like students in a classroom, three of them look like they're part of the same family. The electromagnetic force, the weak nuclear force, and the strong nuclear force, they all play by the rules of quantum mechanics. They may look different on the surface, but once physicists dug deeper, it turned out they could be described with the same kind of mathematical language. This is what gave birth to what's called the Standard Model of particle physics. The Standard Model tells you about quarks and electrons, about photons and gluons, about how particles carry forces. It doesn't explain everything, but it's ridiculously successful at predicting what happens inside particle accelerators and reactors. But in the back of the classroom sits gravity. It doesn't fit the group photo. While the other forces are quantum, gravity still insists on being described in the language of curved spacetime. Physicists have tried to fix this by quantizing gravity, meaning they try to describe it in the same terms as the other forces. If electromagnetism has a photon as its force carrier, maybe gravity has a particle too, a hypothetical particle called the graviton. The idea is simple on paper. The graviton would be a massless particle that travels at the speed of light, carrying the force of gravity just like the photon carries light. Elegant, right? Except when you try to actually do the math with gravitons, everything blows up. The calculations give you infinities that can't be cancelled out, predictions that make no physical sense. This is where theories like loop quantum gravity come in. Instead of treating gravity as just another force, loop quantum gravity says space itself is made of tiny loops, like a woven fabric. On the smaller scales, space-time wouldn't be smooth. It would be pixelated, like zooming into a digital image and suddenly seeing the grid of pixels. The theory is bold, but it's also incomplete. It can handle some parts of the puzzle, like the Big Bang or black hole interiors, but it doesn't naturally include the other forces. Then there are even wilder ideas. Gravity as an emergent force. Some physicists have argued that gravity isn't fundamental at all, but something that emerges from more basic ingredients, like how temperature emerges from atoms moving around. Nobody thinks of temperature particles. It's a property of a whole system. By that analogy, maybe space-time curvature is just the large-scale behavior of something deeper, like entanglement between quantum bits of reality. If that's true, then chasing a graviton might be like chasing the wrong thing entirely. This outsider status of gravity becomes brutally obvious in extreme situations. Black holes are the best example. From relativity's perspective, they're simple. A region where space-time bends so steeply that not even light can escape. But when you add quantum mechanics, something strange happens. Stephen Hawking showed that black holes shouldn't be perfectly black. They should leak radiation through quantum effects at their edge. This Hawking radiation means black holes can eventually evaporate. That's a shocking prediction, but it also creates a paradox. If black holes evaporate, what happens to the information about everything that fell in? Relativity says the information is gone forever. Quantum mechanics says information can't be destroyed. Once again, gravity stands apart, refusing to reconcile with quantum rules. The outsider problem shows up at the other end of the timeline too, the birth of the universe. The Big Bang is where relativity predicts a singularity, but quantum physics screams that singularities can't exist. Something has to give, but we don't know what because gravity won't join the quantum club. This is why so many attempts at a theory of everything get stuck here. It's not that the other forces are easy, they took decades of work, but they at least played by the same rules. Gravity just won't. It insists on standing in the corner, speaking a different language. So every path forward, whether it's gravitons, loops, emergent spacetime, or something else, keeps running into roadblocks. We know gravity can't just stay separate forever, because the universe has situations where it collides with quantum physics head-on. But so far, nobody's been able to translate one language into the other without the whole thing falling apart. And that's the irony. Gravity, The force that holds the universe together is the very thing tearing our theories apart. If there's one idea that captured the imagination of physicists more than any other in the last half-century, it's string theory. For decades, it was hyped as the candidate for a theory of everything. At its peak, it wasn't just a theory, it was almost a movement. Whole departments devoted themselves to it. Books were written claiming it would soon unlock the ultimate secrets, and for a while, it felt like the dream was finally within reach. So, what's the big idea? Instead of treating particles as tiny points, like dots with no size, string theory says the most fundamental building blocks of nature are not points at all, but tiny vibrating strings of energy. Imagine a violin string, but shrunk down so small that even the best microscopes in the universe couldn't see it. The way the string vibrates determines what kind of particle it becomes. A certain vibration might look like an electron, another like a quark, another like a graviton. That's the elegance. One basic ingredient, many outcomes. It sounds beautiful, nature as music, and in theory it could unify everything. The electromagnetic force, the strong and weak forces, even gravity, all coming from the same strings, just vibrating in different ways. That's why so many physicists jumped on board. For once, it looked like we had a single framework that included gravity naturally, instead of treating it like an outsider. But here's where the stumbles began. For string theory to make sense, it requires extra dimensions. Not 3, not 4, but sometimes 10 or even 11 dimensions. These aren't dimensions you can walk through like a hallway. They're curled up, tiny, hidden in ways we can't see directly. Think of them like the threads in a piece of fabric. From far away, the fabric looks flat, but up close, you see the woven threads. String theory says space-time is like that. Extra dimensions woven in so tightly we don't notice them. Great for math, but a nightmare for experiments, because we have no way to confirm they're really there. Then came the problem of the landscape. String theory didn't give one neat solution. It gave an almost infinite number of possible universes, each with different constants, particles, and laws. Instead of narrowing things down, it opened the floodgates. It was like hoping for a single treasure map and instead finding a whole library of maps, with no way to know which one points to the real treasure. This is where critics started sharpening their knives. A theory that explains everything too easily risks explaining nothing. If any universe could fit into the math, then how do you test it? How do you know which one is ours? Some string theorists leaned on the idea of the multiverse, that all those universes exist and we just happen to live in this one because its conditions allow life. But that's a dangerous move, because it shifts the theory from science into philosophy. If you can't test it, is it really physics? Even today, string theory isn't dead. It's evolved into new forms, like M-theory, which ties together different versions of string theory into a bigger framework. It has led to powerful mathematical tools, especially in understanding black holes and quantum fields. But here's the honest truth. After decades of work, it hasn't produced a single testable prediction we can check in the lab. That's why some physicists have grown skeptical. There are still efforts to tie it to real observations. One program called the Swampland Conjecture tries to weed out which string theory universes are realistic and which are pure fantasy. Some papers have even tried to connect string theory to dark energy, the mysterious force accelerating the expansion of the universe. But it's all still indirect. Nothing you can point to and say, that proves strings are real. And that's the tragedy of string theory. It began as the most promising attempt at unification, one that could finally bring gravity into the quantum fold. It had the elegance, the excitement, the momentum. But in the end, it's been more like a beautiful symphony that nobody can play in real life. The math works in its own world, but when you try to line it up with experiments, the music fades. Some say it's only a matter of time before string theory finds its test. Others argue it was a brilliant detour that taught us new math but won't lead to the ultimate theory. Either way, the story of string theory is a reminder. Beauty in physics is seductive, but beauty alone doesn't make a theory true. After decades of string theory and other approaches circling without experimental proof, a shift happened. Physicists began to realize, if we want progress, we can't just sit in the armchairs of theory. We need experiments that actually probe gravity at the quantum level. The challenge, though, is brutal. Gravity is the weakest of the fundamental forces, so weak that, at the scale of particles, it's practically non-existent compared to electromagnetism or the nuclear forces. To put it into perspective, take a paperclip and hold it over the ground. The tiny magnet on your fridge is strong enough to lift it, overpowering the entire gravitational pull of the Earth beneath it. That's how feeble gravity is when you zoom in. So, how do you test it at the quantum scale? This is where creativity comes in. One of the boldest ideas physicists have proposed is to use entanglement as a litmus test. Here's the reasoning. In quantum mechanics, entanglement is a sign of interaction. If two particles become entangled, it means something has linked them. So if two tiny masses become entangled only through their gravitational attraction, that would be evidence that gravity itself is a quantum force. It would mean gravity can create quantum correlations, just like photons or electrons can. This has inspired designs for tabletop experiments. Imagine two ultra-cold spheres of matter, each no bigger than a grain of sand, carefully isolated from every other force. You place them close enough that the only way they can influence each other is through gravity. Then, if they become entangled, if their quantum states become linked, you'd have the first real hint that gravity plays by quantum rules. These experiments push technology to the edge. You need extreme vacuum chambers, cryogenic cooling, and isolation from vibrations so tiny they can ruin the test. Even the faint buzz of the Earth itself, seismic noise, electromagnetic background, can drown out the signal. It's like trying to hear a whisper in the middle of a rock concert. There are other approaches too. Physicists are testing the strength of gravity at microscopic distances, trying to see if it behaves differently when you shrink things down. If it deviates from Newton's inverse square law at very small scales, that could be a clue to extra dimensions or hidden physics. These are called short-range gravity experiments, and they involve delicate setups where tiny masses are brought astonishingly close, while detectors measure the faintest possible tugs. One experiment even used a device resembling a miniature seesaw, balanced so perfectly that the gravitational pull of a small bead could tip it. It's an insane level of sensitivity, measuring forces trillions of times weaker than the pull of a magnet on a paperclip. Then there's the search for quantum signatures in astrophysical phenomena. Black holes, neutron stars, and the cosmic microwave background are natural laboratories where quantum mechanics and gravity collide. For example, if we ever detect Hawking radiation directly, or something like it, it would be a smoking gun for gravity's quantum nature. But these cosmic signals are faint, far away, and hard to interpret. It's like trying to reverse engineer the rules of a game by watching it being played on a screen with missing pixels. The point is this: experiments are finally moving the hunt for unification from the blackboard to the lab. That doesn't mean results will come overnight. These setups are some of the most delicate in the history of science. But the very fact that physicists are building machines to test whether gravity is quantum marks a turning point. It shows we're not just relying on elegant math anymore, we're demanding evidence. Whatever these experiments find, it changes everything. If they see quantum entanglement from gravity, it's confirmation that gravity belongs in the quantum club, and that any theory of everything must respect that. If they don't see it, it could mean we've been assuming the wrong thing, that maybe gravity really does work differently. Either outcome forces a rethink. That's why this stage of the journey feels so exciting. For years, the dream of unification was almost philosophical, out of reach. Now, for the first time, it's something we might glimpse with actual instruments, in actual labs, in our lifetimes. One of the most remarkable discoveries of the last decade was that we can actually listen to the universe through gravitational waves. For 100 years, Einstein's theory predicted them. Ripples in spacetime created whenever massive objects accelerate violently, like two black holes colliding. But it wasn't until 2015 that LIGO first caught their signal, and since then detectors have been picking them up like cosmic whispers. At first it seemed like these detections were just confirmations of relativity, and they were, down to incredible precision. The signals matched Einstein's equations almost perfectly. But soon, physicists realized something bigger. Gravitational waves might be the ultimate stress test for any theory of everything. They let us probe gravity in conditions no lab could ever recreate. Black hole collisions, neutron star mergers, supernovae. These are natural experiments that push both relativity and quantum mechanics to their limits. Here's why this matters. Many alternatives to relativity, modified gravity theories, extra dimensions, even some versions of string theory, predict that gravitational waves should behave differently than Einstein said. For example, some predict that gravitational waves should have extra flavors, called polarizations. Einstein's version only allows two kinds, like two possible orientations of a ripple. But in certain rival models, you'd expect scalar waves or vector waves, almost like hidden channels of vibration running through spacetime. So physicists have turned LIGO, VIRGO, and now KAGRA into truth detectors. Every time a new gravitational wave rolls in, they check, do we see any extra polarizations? Any deviations from the speed of light? Any distortions that shouldn't be there? So far, the answer has been no. And that's devastating news for many theories that try to expand or replace relativity. Whole families of models are being quietly cornered out of existence because they would have required signals we simply aren't seeing. But the real test is still coming. As detectors get more sensitive, we'll start to pick up more subtle effects. For instance, if gravity interacts with quantum fields differently at extreme energies, it might leave tiny imprints in the waveforms, slight distortions in how the waves rise and fade. Some teams are already combing through data, looking for anything that doesn't quite match Einstein's predictions. It's like looking for a tiny crack in a perfect piece of glass. And then there's the stochastic background, the hum of gravitational waves from countless ancient events overlapping across the universe. If we can measure that background in detail, it could tell us whether new physics is hiding at cosmic scales. Some theories predict that the early universe should have flooded space with exotic gravitational waves, superluminal ripples, or waves linked to unknown fields. If those signatures aren't there, those theories collapse. If they are, we'd have a window into physics far beyond the standard model. Here's the paradox. So far, Einstein keeps winning. His equations still describe the universe with stunning accuracy, even in the most extreme conditions we've tested. For a century-old theory, that's almost embarrassing for modern physics. Every time we think we've found a crack, it turns out relativity still holds strong. It's like building newer, more powerful flashlights to search for flaws, and all we keep finding is that the glass is spotless. But physicists aren't giving up, because they know there must be new physics out there. The early universe, black hole evaporation, quantum foam, all demand a unification. Gravitational waves are simply the best probe we have right now, the one instrument that lets us check what happens when gravity goes wild. Think of it like this. If relativity and quantum mechanics are two musical instruments that can't play in tune, then gravitational waves are the orchestra performances where you can hear the disharmony, if it's there. So far, the instruments keep sounding perfect, but eventually, if the discord exists, this is where it will show up. And that's why gravitational waves are not just an incredible discovery, they're a doorway. Every detection is both a victory lap for Einstein and a silent interrogation of every rival theory. One day, maybe, one of those waves will carry the note that doesn't fit. And when that happens, we'll finally know which path leads closer to a true theory of everything. One of the strangest features of modern physics is how often scientists fall in love with beauty. It might sound odd, but equations have an aesthetic quality. When they're simple, symmetrical, and elegant, they feel right. Einstein himself once said that a good theory should be beautiful, and to be fair, history seemed to prove him right. Relativity is elegant. Maxwell's equations for electromagnetism are elegant. Even the Schrödinger equation has a kind of neat simplicity. Beauty and truth seem to walk hand in hand. But here's the trap. The universe doesn't care about what we think is beautiful. And over, physics has been reminded of that fact. Take supersymmetry, for example. For years, it was touted as the natural extension of the standard model. The math was gorgeous. Every known particle had a heavier superpartner. Quarks had squarks, electrons had selectrons, neutrinos had sneutrinos. The symmetry tied everything together in a neat bow, and it solved multiple problems at once. It explained dark matter, stabilized the Higgs boson, and made string theory possible. On paper, it was almost too perfect. But then came the tests. When the Large Hadron Collider finally roared to life, one of its top goals was to find evidence for supersymmetric particles. Physicists thought they'd show up quickly because the theory suggested they'd be within reach of the collider's energy. Years went by, petabytes of data were sifted, and nothing. No squarks, no selectrons, no supersymmetry. The beautiful theory just wasn't showing up in reality. This isn't the first time beauty seduced science. Think back to the idea of crystalline spheres in ancient astronomy. The Greeks thought the heavens must be perfect, so they built a model with nested spheres carrying planets in flawless circles. It was beautiful, but it was wrong. The real orbits were messy ellipses, as Kepler eventually discovered. Nature didn't care about perfect circles, it cared about what actually worked. Today, we're facing the same dilemma on a grander scale. String theory, supersymmetry, grand unification, they all have that aesthetic charm. They appeal to the human desire for symmetry and order. But experiment after experiment has shown us that beauty isn't a guarantee. The universe has no obligation to align with our sense of elegance. The danger of chasing beauty is that it can blind us. If a theory looks so elegant that you fall in love with it, you might ignore the fact that it isn't testable or that its predictions don't match data. Physics becomes less about describing reality and more about admiring a mathematical work of art. And that's risky, because science only survives when it's grounded in evidence. There's also a psychological angle. Physicists are human, and humans crave patterns. We want the world to make sense, to have symmetry and order. But what if the universe doesn't care about our cravings? What if it's fundamentally messy or based on principles that don't align with our idea of beauty? That possibility is uncomfortable, but it might explain why every elegant attempt at a theory of everything keeps failing. Einstein himself fell into this trap in his later years. He rejected quantum mechanics partly because he thought the randomness and uncertainty were ugly. He wanted a deterministic universe that was neat and logical, as we discussed earlier. But reality kept proving him wrong. Quantum mechanics might not have been pretty in Einstein's eyes, but it worked. And it still works better than anything else we've built for the microscopic world. So, maybe that's the real lesson here. Physics doesn't advance by chasing beauty, it advances by chasing truth. Sometimes the truth is elegant, like relativity. Sometimes it's messy, like the standard model, which is basically a patchwork of particles and constants with no clear unifying story. But messy or not, it's the one that matches reality. This tension between beauty and truth is one of the reasons the theory of everything has been so elusive. Theories that look right often collapse under the weight of experiments. And the theories that actually work, like the standard model, don't look like a masterpiece at all. They look like a kludge, a strange collection of fixes and parameters. But that's physics. It's about what nature gives us, not what we wish it looked like. When people talk about the failures of a theory of everything, it can sound like physics has been spinning its wheels for decades. But that's not really true. Even though no single framework has tied everything together, the search has produced breakthroughs that are powerful in their own right. They're not the grand prize, but they're victories along the way. Tools, insights, and fragments of unification that actually work. Take the conformal bootstrap program. It started as an abstract idea in the 1970s by Alexander Polyakov, but in recent years it's exploded into one of the most precise ways we have of understanding quantum field theories. Instead of trying to write down every detail of a quantum system, the bootstrap works by locking down what's possible and what's not, using symmetry and consistency alone. It's a bit like solving a puzzle without ever seeing the picture on the box. You just know the rules about how pieces can fit, and by applying them carefully, the solution starts to emerge. With the bootstrap, physicists like David Simmons-Duffin and David Poland have pinned down properties of quantum fields to astonishing precision. It's not the theory of everything, but it's proof that the methods we're inventing in the chase can map out vast swaths of physics we never understood before. Then there's the work on scattering amplitudes. This is the study of how particles bounce off one another in high-energy collisions, the kind you see in particle accelerators. Traditionally, calculating these interactions was a nightmare of algebra. Pages and pages of terms that seemed to stretch forever. But in the last couple of decades, physicists have discovered that underneath all that mess, there's a hidden simplicity. Amplitudes can often be written in shockingly compact forms, using geometric shapes like polytopes. Imagine turning a chaotic brawl of equations into a single, elegant drawing. Another major partial victory is holography, specifically the ADS/CFT correspondence proposed by Juan Maldacena. It's a mouthful, but the idea is simple to describe. A universe with gravity in it can sometimes be exactly equivalent to a universe without gravity living on its boundary. It's like saying everything happening inside a room can be fully described by information painted on the walls. That sounds bizarre, but the math works out, and it's given physicists a completely new way of thinking about spacetime. It doesn't unify everything, but it shows that gravity and quantum theory might be two sides of the same coin, connected in ways we never suspected. Each of these breakthroughs, bootstrap, amplitudes, holography, are like tools we've picked up while trying to climb a mountain. Maybe they don't take us to the summit, but they let us scale cliffs that used to look impossible. They've also reshaped how physicists think about the problem itself. Instead of imagining one grand theory falling from the sky, maybe the answer lies in stitching together these fragments into a bigger picture. But there's a catch. None of these partial victories tells the whole story. The bootstrap is powerful, but it doesn't naturally include gravity. Amplitudes reveal hidden simplicity, but we don't yet know how to translate that into a framework that unifies all forces. Holography is stunning, but it's limited to special kinds of universes, not the one we actually live in. It's like having pieces of different puzzles, each beautiful on its own. But when you try to assemble them, they don't quite form a single picture. Still, these successes matter. They show that even in the absence of a theory of everything, physics isn't standing still. Every time a grand idea stumbles, it leaves behind methods that push us forward in unexpected ways. It's progress, even if it doesn't come wrapped in the package we were hoping for. Here's one way to think about it. Imagine explorers trying to find a single river that connects two great oceans. They never find the mythical river. But in the process of searching, they discover new mountains, new valleys, new streams that no one knew existed. Even if the river doesn't exist, the map of the world becomes richer. That's what these partial victories are doing for physics. And maybe that's the real secret. A theory of everything might not arrive as one clean equation delivered all at once. It might emerge slowly, pieced together from these smaller wins. The bootstrap, amplitudes, holography, quantum gravity experiments, gravitational wave observations. Each is like a shard of glass. On their own, they're incomplete. But when you hold them up together, you start to see a pattern forming. Up to this point, we've been talking about technical challenges. The math blowing up, the experiments being hard, the theories refusing to fit. But there's another side to why a theory of everything keeps slipping away. It isn't just about the equations, it's also about the questions we're asking. Maybe the reason every attempt has failed is because we're chasing something that doesn't even exist in the way we imagine. Think about it. The phrase theory of everything makes it sound like there's a single, final equation that explains every detail of the universe. One formula to rule them all. But is that actually how reality works? Or is that just our human bias for neatness and closure? This is where philosophy crashes into physics. On one side, you've got the dreamers who believe nature must have unity at its core. On the other side, you've got the skeptics who point out that reality might be too complex or even too inconsistent for a single theory to cover it all. Consider Gödel's incompleteness theorems. They weren't written for physics, they came out of mathematics in the 1930s. But their message is sobering. In any system of logic rich enough to describe numbers, there will always be true statements that can't be proven within that system. In other words, no matter how good your rules are, there will always be truths they can't reach. If that's true for math, why wouldn't it be true for physics? Maybe the universe can't be captured by one self-contained theory. Maybe there will always be truths beyond the reach of any framework we invent. Another roadblock is the very meaning of everything. Does it mean just the fundamental forces and particles? Does it include consciousness, life, the arrow of time? The more you stretch the definition, the less likely it is that one equation can handle it all. Physicists might be chasing a theory of everything physical, but people often hear it as a theory of literally everything. That gap in interpretation fuels endless debate. Even the concept of laws itself raises questions. We often think of the universe as running on rules, like a computer runs on code. But is that assumption correct? Some philosophers argue that what we call laws of physics are just descriptions of patterns we see, not laws written into reality itself. If that's true, then a theory of everything wouldn't be the source code of the universe. It would just be a very clever summary of regularities we happen to notice. There's also the problem of scale. Maybe there isn't one set of laws that work everywhere. Maybe reality is layered, with different rules applying at different levels. Think of how biology has rules that don't exist in chemistry, and chemistry has rules that don't exist in physics. Life emerges from atoms, but you don't need to mention DNA when you're describing how electrons move. Why should the universe be any different? It could be that relativity and quantum mechanics are simply the right tools for their respective domains. And expecting a single framework to unify them is like demanding one tool that works as both a microscope and a telescope. Useful in theory, impossible in practice. Then there's the possibility that we're limited by our own minds. Our brains evolved to hunt, gather, and survive, not to grasp the fabric of spacetime. We've stretched our imagination through math, experiments, and technology, but maybe there are limits to what we can ever comprehend. Imagine a dog trying to understand calculus. It just isn't wired for that. What if we're in the same situation with the ultimate laws of physics? The universe may be running on principles we'll never truly wrap our heads around, no matter how advanced we get. That doesn't mean the search is pointless. Far from it. Every failed theory teaches us something. Every experiment that comes up empty still rules out possibilities. But philosophically, it forces us to ask, what are we actually hunting for? Are we chasing a final equation that doesn't exist? Or are we building a never-ending ladder, one rung at a time, where the climb itself is the real achievement? This is why some physicists, like Sabine Hossenfelder, have argued that the obsession with unification is misplaced. Instead of forcing everything into one framework, maybe we should accept that the universe is patchwork, messy, irregular, but still describable in pieces. Others push back, insisting that history shows unification is always the right path. Newton unified the heavens and earth. Maxwell unified electricity and magnetism. The Standard Model unified 3 of the 4 forces. Why stop now? So we're caught between two philosophies. One says the quest is noble and necessary. The other says it may be futile, maybe even misguided. And neither side can prove the other wrong, because the answer might depend not just on physics, but on the very structure of knowledge itself. In the end, these philosophical roadblocks may be as formidable as the mathematical ones. They force us to confront uncomfortable questions. What if everything can't be put in a box? What if the dream itself is more of a human desire than a cosmic reality? And if that's true, would we even recognize the theory of everything if it was staring us in the face? When a problem refuses to give way after decades of effort, you eventually start looking beyond the usual paths. That's exactly what's happening in physics right now. Since traditional approaches to a theory of everything keep stalling, some researchers are taking the bold step of asking, what if we've been thinking about it the wrong way entirely? One of the most intriguing shifts is the idea that spacetime itself might not be fundamental. In other words, the fabric of space and time, the very stage where everything plays out, could actually be built from something deeper. Think of how temperature isn't fundamental. There are no temperature particles. Temperature is an emergent property of countless atoms jiggling around. In the same way, some physicists argue that space and time emerge from patterns of quantum entanglement. This perspective has been championed by scientists such as Mark van Ramsdonk. Others like Eric Verlinde have gone further, suggesting gravity and space-time are emergent phenomena rather than fundamental forces. Instead of space-time being the foundation, it could be more like a web woven from the connections between quantum bits. If that's true, then the quest for a theory of everything might not be about unifying two separate systems. It might be about realizing that space-time was never fundamental to begin with. Then, there's the idea of the holographic principle. We touched on it earlier with ADS/CFT, but its implications go much further. It suggests that our entire universe could be described by information encoded on a boundary, a kind of cosmic hologram. The 3D reality we experience might actually be a projection of 2D information. It sounds outrageous, but it's not just science fiction. Mathematically, the principle is consistent, and in certain contexts, it works beautifully. If it applies to our universe, then the whole idea of unifying relativity and quantum mechanics might be rephrased in terms of information theory rather than geometry. Instead of space-time and matter being the raw ingredients, the universe at its core might just be data. Another wild proposal is the causal set approach. Instead of treating space-time as continuous, it imagines space-time as a network of discrete events linked by cause and effect. Imagine a constellation of points, where each point represents an event, and arrows connect them in the order they influence one another. In this picture, space and time are nothing more than the structure of this causal network. Smooth space-time emerges when you zoom out, just like a smooth beach looks continuous until you notice it's really made of grains of sand. There are even proposals like twistor theory, Roger Penrose's brainchild, which tries to rebuild physics from geometric structures that look nothing like our usual picture of space-time. Twistor space treats events not as positions in space and time, but as relationships defined by light rays. It flips our perspective completely. Instead of space and time being the foundation, the paths of light themselves define reality. And then there's the ever-provocative simulation hypothesis. What if the reason we can't unify everything is because we're not looking at the universe itself, but at the rules of a simulation? In a video game, you can see water flowing, trees swaying, and characters moving, but underneath it all is code. The physics of the game isn't the fundamental truth. It's just the surface behavior of instructions running on a machine. If our universe is like that, then maybe relativity and quantum mechanics are just subroutines of a bigger system, never meant to line up perfectly because they were designed for different tasks. Now, most physicists don't take the simulation hypothesis as a working scientific theory. It's hard to test and it quickly veers into philosophy. But it serves as a useful reminder. Maybe the conflict we see between our theories is a clue that the rules we're studying aren't the deepest rules after all. Another new direction is more practical, using quantum information theory as a guide. Instead of trying to mash equations together, some physicists are asking, What are the rules of information flow in the universe? If you follow the logic of how information can be stored, transmitted, and conserved, maybe the rest of physics will fall into place. This approach is already reshaping how we think about black holes. The black hole information paradox has driven people to realize that unification might not be about particles and fields at all. It might be about ensuring that information is never lost. What ties all these ideas together is their willingness to step outside the box. They don't start from the assumption that space-time or particles or even forces are the most fundamental ingredients. Instead, they treat those things as emergent, appearances that come from something deeper. It's a radical shift, but history shows that revolutions often come from daring to throw out the assumptions everyone else takes for granted. Still, these wild ideas face the same problem as the more conventional ones: evidence. They're creative, they're mathematically rich, and they open doors to new ways of thinking. But until we can design experiments that test them, they remain speculative. Just like string theory, they risk floating in the realm of elegant thought experiments. The question is whether any of them can cross that gap, from beautiful speculation to measurable reality. If one of these new directions can suggest an experiment that proves or disproves it, then it might finally push the search for a theory of everything into new territory. Until then, they're like trail markers in a foggy forest. They point to possible paths forward, but we can't yet see where those paths lead. When you hear that every attempt at a theory of everything has failed, it's tempting to think of the story as one long list of dead ends. But that's not the right way to see it. In science, failure isn't wasted time. It's part of the process. Every time a grand theory stumbles, it leaves behind tools, insights, and even whole new branches of physics that never would have existed otherwise. Think of Newton. His laws weren't perfect. They eventually failed to explain Mercury's orbit and the bending of light. But those failures gave birth to Einstein's relativity. Or take quantum mechanics itself. It arose because classical physics failed to explain the behavior of atoms. In both cases, the breakdown of old theories wasn't a tragedy, it was the spark that lit the next fire. The same thing is happening with the search for unification. String theory hasn't given us the theory of everything, but it's produced powerful mathematics now used in fields as diverse as condensed matter physics and pure geometry. Attempts to quantize gravity haven't yet succeeded, but they've sharpened our understanding of black holes and early universe cosmology. Even when the big dream falls short, the side effects keep pushing science forward. This is why scientists don't just shrug and walk away when a unification theory collapses. Instead, they adapt. They take what worked, discard what didn't, and move forward. Loop quantum gravity may not unify everything, but its idea of spacetime having a discrete structure has influenced thinking across many areas. The holographic principle might not be the ultimate answer, but it's provided insights into how gravity and quantum mechanics might be linked through information. These are stepping stones, not final destinations. Another reason failure isn't really failure is that it teaches us humility. Science has a way of reminding us that the universe isn't obligated to follow our expectations. Supersymmetry didn't show up at the Large Hadron Collider, despite how neat and tidy it would have been. That disappointment forces physicists to rethink, to ask harder questions, and to look in directions they might have ignored otherwise. In a sense, the universe is steering us by saying, "Not here. Try again." It's also worth remembering that science doesn't have to end with one final equation. Progress comes in layers. Maybe we'll never have a neat theory of everything, but that doesn't mean we won't build better and better frameworks that cover more ground. Relativity didn't invalidate Newton. It expanded it. Quantum mechanics didn't wipe out classical physics. It added to it. Each step builds on the one before, even if none of them is the final truth. In fact, there's an argument to be made that the failures are what make physics exciting. If we already had the theory of everything, the story would be over. There would be no mysteries left, no new questions to chase. The fact that we keep failing means the story continues, and every generation gets to add to it. It's frustrating, but it's also what keeps the field alive. So, when you look at the long trail of failed attempts, from Einstein's unified field theory to string theory's infinite landscape to countless other models, you could call them disappointments. Or you could see them as the scaffolding of progress, each one lifting us a little higher, even if the top is still hidden in the clouds. Failure in physics isn't the end of the road, it's the road itself. So, after all of this, decades of theories, experiments, dead ends, and breakthroughs, we're still left asking, why does every theory of everything keep failing? The simple answer is that the universe is more stubborn than our expectations. It refuses to fit neatly into one framework. Every time we think we've boxed it in, it finds a way to remind us that it's bigger, stranger, and more layered than we imagined. But here's the thing. Maybe that's not a failure at all. Maybe it's the point. Think about how far we've come just by chasing this dream. We've gone from Newton's apple to Einstein's spacetime, from Bohr's atom to quantum fields buzzing with particles. We've built detectors that can hear black holes colliding a billion light years away. We've designed experiments sensitive enough to measure the tiniest pull of gravity on microscopic objects. None of these achievements would exist if physicists hadn't been stubborn enough to keep chasing a theory of everything, even when it kept slipping through their fingers. The failures are real, but so is the progress. Each collapse, Einstein's failed unification, string theory's landscape problem, supersymmetry's absence at the LHC, has left us with new tools, new math, and new ways of seeing the world. The road hasn't led to the final theory, but it has led to discoveries that reshape how we live and how we think. And maybe we've been asking the wrong question. Maybe the universe isn't meant to be compressed into a single line of math. Maybe it's more like a vast library. Each theory is a book describing one part of the story. Relativity tells the tale of the cosmos on grand scales. Quantum mechanics tells the tale of the microscopic. The Standard Model maps the forces inside atoms. None of them is the whole library, but together they give us a richer picture of reality than we had before. There's also something deeply human about this endless chase. We're not just solving puzzles for their own sake, we're trying to understand our place in the universe. If we ever did find a true theory of everything, it wouldn't just be a scientific triumph, it would be a philosophical one. It would tell us whether the universe is ultimately simple or irreducibly complex. Whether order underlies the chaos, whether the deepest layer of reality is geometry, information, or something we haven't even imagined yet. And maybe we will find it. Maybe one day, experiments with quantum gravity will crack the code. Maybe gravitational waves will carry the first hints of new physics. Maybe some radical new framework, emergent spacetime, causal sets, holography will suddenly click into place. But even if we never do, the search itself has value. Because in chasing it, we uncover truths we wouldn't have found otherwise. The endless horizon of physics isn't a sign of failure, it's a sign of depth. Every horizon you reach just reveals another one further away. It's like sailing across an ocean that never ends, frustrating at times, but also exhilarating, because it means there's always more to discover. So, why does every theory of everything keep failing? Because we're not at the end of the story yet. The universe is vast and our understanding is still young. The failures aren't a verdict, they're an invitation. An invitation to keep asking, keep testing, keep exploring. And maybe, just maybe, that's the real theory of everything. Not a single equation, but the unending human drive to understand.